So my name is Thomas Padioleau. I work at the Maison de la Simulation Laboratory at CEA near Paris. And so today I will be presenting DDC, Performance Portable Library, Abstracting Computation on Discrete Domains. So this is a joint work with many people that I summarized with the Gisela team and the Sexa team. So this starts with the Gisela application. That is a plasma physics application for nuclear fusion that studies core turbulence in tokamaks. The main object that they manipulate in this application is called the distribution function that lives in a high-dimensional space. So you have, for example, 1 dimension for the species, 3 dimensions in space, 3 dimensions in velocity, and 1 dimension in time. This object is the solution of the Vlasov-Poisson equations that they solve in the gyrokinetic approximation to reduce by 1 the number of dimensions to be able to tackle this equation. This is the Gisela application is a 30 years old Fortran 90 code that is not that large. We count roughly 40,000 lines of code of Fortran code, and that is developed by a team at CEA in the south of France in Cadarache. Regarding parallelism, they use quite classical softwares, so MPI for the distributed memory parallelism, and OpenMP for the shared memory parallelism. It runs still efficient simulation on hundreds of thousands of cores and consuming 100 million of CPU hours. But a few years ago, we needed to rework Gisela to be able to be prepared for the exascale computing, so to be able to work on multiple vendor GPUs, to run on other CPU hardwares like the ARM x64. We needed also to rework the application to handle more realistic geometries for the tokamak. And to handle multiple geometries or meshes that were not available yet in the application. But we realized that it was difficult to make changes in the application due to a lot of implicits that were only known to the experts of the software, and making it difficult to make changes for non-experts of Gisela. So as an example of implicit that we faced was the use of multiple representations of the distribution function, that they use a lot of Fortran arrays in the application. And the distribution function can sometimes, depending on the stage of the numerical scheme, have a spline representation, that is meaning that we store in the array spline coefficients that represent coefficients on a spline basis, that is a polynomial basis. Otherwise, other representation, that is the Fourier representation, and they store Fourier coefficients, or otherwise a pointwise representation of the distribution function. And all of that is only appears as arrays in the source code, making it difficult to know what is expected, what representation is expected when calling functions. Same question with the meshes that take the form of arrays, whether they are uniform or non-uniform. And it's difficult, again, reading the source code, whether it is expected a uniform or non-uniform mesh. Another kind of implicit that we faced was the way we iterate over arrays using, we have a lot of dimensions, as I said, so a lot of nested loops, and we are using raw integers for Fortran, and it was difficult without knowing well the code what the integers represent, whether they represent a point in a mesh, a face, or a cell. Does it represent a local index or a global index when we regarding distributed memory parallelism, or again, does it account for a halo zone when we have stencil computation? So all of this information is difficult to get when only reading the source code, and that led us to rewrite the application from scratch in C++ so that leveraging the DDC library to bring closer to the data all the metadata that was missing in the source code. So that brings us to DDC. That is a C++ library that is inspired by the xarray Python library. So the xarray library is built on top of NumPy and uses new containers that will label the dimensions so that they have a more meaningful representation for the user and associate data to what they call coordinates. So we want the same kind of features in DDC, but with a minimal overhead or zero overhead, meaning that we will be labeling the dimensions at compile time. As we are here in the Kokkos user group, we are based on Kokkos so that we can get a performance portable library for the core multidimensional algorithm that will iterate over our data structures. So let's dive into the core concepts of the library. And I will start with the discrete element concept. So as I said, we want to label dimensions at compile time, and it takes the form of defining structures for each dimension. So here, for example, we have the struct ddimx and struct ddimy. So these two tags will represent dimensions in the arrays. Then a discrete element, an instance of a discrete element will represent a unique element in the dimension, here ddimx. So you can think of ddimx as a dimension of points. So an instance of discrete element ddimx will represent a unique point in this mesh. The discrete element behaves as similarly to a point in an affine space, and we therefore define also discrete vector that will represent semantically represent a vector as in a vector space. So we have also some algebra defined between the two discrete element and discrete vector, addition, subtractions. So we have discrete elements, and we want to also define ranges of discrete elements. We have different ways to define discrete element ranges, depending on the properties that we want, whether they are contiguous sets of discrete elements or a strided step discrete element, discrete domain, or an explicit list of discrete elements. We can form, we can iterate over the discrete elements in a domain, in a set of discrete elements. For example, if we have the discrete domain over ddimx, called domx, then we can use the range-based for loop to iterate over the discrete elements. So you will be, for example, if ddimx will be still, again, a dimension of points, you will be iterating over the points in this domain. And to get to a multidimensional domain, you just add in the template parameters of the domain a new tag, ddmy, for example. And the final concept that I wanted to, the core concept that I wanted to introduce was the notion of attributes. So we call attributes any data that is attached to an instance of either a discrete element, a discrete domain, for example, or the dimension itself. We make a distinction between mutable attributes that are only associated to discrete elements that will be typically arrays, or immutable attributes that are typically attributes that are known after the initialization and that will not evolve during the simulation. So if we focus on the mutable attributes, we introduce two containers, chunk and chunk span. So chunk will be an owning container and chunk span a non-owning container, similar to mdspan. And they behave similarly to the xarray.DataArray structure container. So the idea is that we associate to any discrete element in a domain some data. So for example, we have the chunk example where we allocate some data, some double data over a discrete domain, a contiguous set of discrete elements on a domain that is called domxy. We have two ways to to access the data from this container. We have the associative access, similarly to the X-ray container, where we pass a discrete element. So you have to read it as, I want the data that is associated to a point in the mesh, whatever the position of this discrete element in the set of discrete elements. And we have the second, more classical array access, where we typically want the first or second data in a dimension, whatever discrete elements or points it represents in the domain. We have some slicing features, similarly to MDSpan or Kokkos view, where we have a bracket operator that will that is overloaded to represent the slicing. So we can slice with a discrete element that will remove some a dimension, or a slicing over a discrete domain that will shrink the container. And we get back here a chunk span because it is now a non-owning container. One nice thing that we have with the strong typing of the indices is that we can pass them in any order when accessing the data. So if we have LMX, LMY, and LMXY, so a two-dimensional element, we can pass them with the first three lines at the bottom, reference the same element in the container. Whereas if we are missing the Y component, for example, it will be detected at compile time that one component is missing. So we have multidimensional algorithms to be able to loop over our data structures that are similar to the Kokkos experimental algorithms. So they have we have the parallel versions and the sequential version, and we'll take optional arguments like a string and execution space. And in DDC, they will take either a chunk span or a domain over which to iterate. So the list is given here. We have a parallel for each, a transform reduce, a fill, and a copy. And all of them are implemented, are deferred to Kokkos as an implementation. And the final concept that I wanted to introduce, that is a more work in progress concept, is the notion of discretization that we define as a generator of discrete dimensions. So DDC provides some of them that are linked to the main application that we support, Gisela. We have the uniform point sampling, for example. And the idea is that we can predefine some discrete dimensions that will allow the user to reuse some static attributes, the immutable attributes that I mentioned earlier. So for example, in the case of the uniform point sampling, this will define a function called coordinates that will get the physical location of the point, like a double, giving the position associated to the discrete element on DDMX, if DDMX is a uniform point sampling. I wanted to finish this presentation with an example, so to give you a concrete example view of the DDC library. So with the heat equation in two dimensions, in two spatial dimensions. So we start by defining some structures, X, Y, and T. Oops, sorry. That will represent the continuous dimensions that we discretize with a uniform point sampling for all of them, X, Y, and T. So that gives us DDMX that is defined as a uniform point sampling over X, the same for Y and T. Then there is a phase of initialization that will initialize the immutable attributes, so like the coordinates of points, and give us back some discrete domain that is the list of points that we will be working on. We have some memory allocation, so we associate data, so the temperature field, to the points in the mesh. So we are using chunk, and we pass the discrete domain that we just got from the initialization, and an allocator to specify that we want to work on the device. And the main time loop looks like this. So the first loop over the time steps over a time domain. We can get the current time calling the coordinate that has been defined by the uniform point sampling. We have some boundary condition then with the parallel copy function. And we have the main intensive loop over space, the final parallel for each, where we pass the string, the domain of the output array that is not accounting for the halo zone. And we pass a lambda that the first argument is the discrete element, so a unique identifier for each point in the mesh. And we apply then the numerical scheme of the heat equation. So we have, it looks like is as simple as a Kokkos implementation, but with type safety provided by DDC. So as a conclusion, I wanted to show you that some structured problem can hide implicits in the source code. And using DDC, inspired by the Python library xarray, we could remove some of these implicits by introducing some labeled dimensions at compile time to avoid any overhead, and providing also an associative access to have a more meaningful access to the data manipulated by the user. Thank you, and so the project is open source, is on GitHub. We have a Slack channel and a website that is also a work in progress. Thank you for your attention.
We are very tight on time. Maybe we can have one quick question while setting up. How much does the compile time increases if you do those from typing and you are interested in a lot of different combinations, for example, in the data?
I don't have any measurement for that, but for sure it increases the compilation time because all of our structures becomes unique because of that. So yeah, it increases the compilation time. I don't have any measurement. Sorry? We pay the cost of increasing the compilation time, yeah, for sure.